So we have here a series compound bar, and what that means, it's just simply the fact that we have two different materials. So right here we have a steel bar in red, and it's connected to an aluminum bar right there in gray. And because they're connected end to end, we class them to be compound bars in series. Now, to do our calculations, what we need to find the direct stress in each of the materials, and we also need to find the overall extension for the entire connections. Now, we have some valuable metrics to work with. We have a tensile force right there of 150 kilonewtons. We also know that the shapes are circular, so that's 50 mil for the aluminum bar, and we also have this 20 mil for the steel bar. Now, other important metrics that we have the modulus of elasticities, and that's for the steel, which is 200 gigapascals right there, and 70 gigapascals right there for the aluminum. And that's more than enough for us to actually do this calculation. So what we're going to start with, we're going to find the stress in each of the materials, and the formula we'll start off with is this one. So stress is equal to force divided by area. So that's what we want to use ultimately. So let's start off with the steel bar and work our way through. And we're going to start by finding the stress in the steel bar and the stress in the aluminum bar. So of course, I've said that the formula we want to use is stress equals force divided by area. So what that means is we need to first find the area that we need for the steel. And I'm going to stick to the pi d squared divided by 4. I know that some of you like pi r squared, but in this instance, I'm going to use pi d squared over 4. So that's pi multiplied by 20, and square that and divided by 4. So that gives us the area for the steel bar, and that works out to be 314.16, and I'll keep the millimeters squared for now. Now, if we go for finding the stress in the steel, then we're going to go to our formula now, which is the force divided by area. And just before we do that calculation, I'm really passionate about growing this channel, and that's why I upload at least 5 videos per week on weekdays. And I would like to reach as many people as possible, and to do that it requires your support. So I'm kindly asking you if you could subscribe to the channel or give the video a thumbs up, and that will help out massively, and I thank you for doing so. So back to the calculation. So we are going to do our stress equals force divided by area. We now have the area. We already have the stress from the question, which is 150 kilonewtons. So 150 times 10 to the 3. That's what we will divide by the 314.16. And that will give us the stress then for the steel bar. And that in megapascal terms is 477.5 megapascals. So that right there is one of our calculations done. So we're now going to find the stress in the aluminum bar. And for this one, we again need to find out what the area is. And once more, we're using pi times our diameter squared and divided by 4. And that gives us an area for the aluminum bar of 1963.5 mil squared. So now to find the stress. So it's the same force that we'll use. So that's going to be 150 kilonewtons divided by 1963.5. That gives us 76.4 megapascal. So that takes care of the stress in the aluminum bar. That takes care of the stress in the steel bar. So now let's see how to find the extensions. So for the extensions, I'm going to first derive the formula. And to do so, I want you to bring your attention to this formula, where if we think of the Young's modulus formula as stress divided by strain, because it's a ratio of stress and strain. So we're going to break this down into each of the formulas for stress and strain. So for stress, we use force divided by area. And we're going to divide by now the formula we use for strain, which is change in length divided by initial length or original length. So what we end up with now, if we were to just tidy this up, is force divided by area. And if we change our division sign there to a times, we end up with our original length divided by our extension. And we know that it's the extension that we're trying to find. So all we have to do now is to just rearrange this so we get the extension as this subject. And what that will look like is our force times our original length and all divided by the modulus of elasticity multiplied by area. So all we have to do now is just to put these in the formulas and we'll get our extension. So let's do that now. So let's start with the extension for steel and what's that going to look like. So we have our force, so that's 150 kilonewtons. We know the original length for the steel. I'm going to convert it to mil, so that's 300, and all divided by the modulus of elasticity, so that's 200 times 10 to the 9, and multiplied by the area, which is 314.16. So that gives us an extension of 0.716 millimeters for the steel. And we're going to repeat the process now, but this time it's going to be for the aluminum. So in this instance, force still the same, so 150 times 10 to the power of 3, multiplied by our original length, which is 200, and all divided by modulus of elasticity, so 70 gigapascal, times 10 to the 9 times our area, and so that gives us an extension of 0.219 millimeters. So what we need though is the total extension. So the overall extension is going to give us just the sum of those two, so 0.716 plus 0.219. That gives us 0.935 millimeters. So that's our overall extension. Now another very important topic that complements this one is compound bars, but this time in parallel structure. And if you'd like to learn about that, then check this next video out.